The gradient of x squared over 2 minus y squared over 2 is this function, vector valued function. X in the first component, negative y in the second component. I'm going to draw that below in red, along with the level sets of this function right here. The level sets, I'm going to name LC, are the sets of this form. Ordered pairs of numbers, x, y, such that x squared minus y squared is equal to 2 times c. I've just moved the 2 to the other side. Now, thinking about the various values of c, when c is 0, I have x squared minus y squared is equal to 0, x squared is equal to y squared. That could either mean that y is equal to x, giving this line, so I'll label that L0, or y is equal to negative x, so I put this line in, that's also L0. So I've got these two lines this way, y is x and y is negative x. The solution set to those two equations both make up L0. When L is 1, thinking about this, when C is 1, x squared minus y squared is equal to 2. Well, that certainly means that x squared has to be bigger than y squared, so x has to be bigger than y. So L1 is out here in the x is bigger than y region, and I know that it is a hyperbola. And let me think for a second about what point this would pass through. L1 would have to contain the point, let's see, when y is 0 and c is 1, x squared has to be 2, so x has to be square root of 2. Square root of 2 comma 0 is on L1, and similarly over here on the other half of L1 I have the point negative square root of 2 comma 0. Okay, and then similarly on L2 right there, that is x squared minus y squared is 2 times 2, that's 4. So when y is 0, x has to be such that x squared is equal to 4, or simply 2 right there. Okay. And this point right here then is negative 2 comma 0. Okay, and then I wanted to do some of the LCs with negative values of c, say L negative 1. If this is x squared minus y squared is equal to negative 2, then y squared needs to be bigger than x squared. The place where the y values are bigger than the x values is up here, and the place where the y values are smaller than the x values is down here. And L negative 1 again has two components. Just to be thorough, let me figure out the coordinates of that point. That has a x-coordinate of 0 and a y-coordinate of square root of 2, doesn't it? And this down here is 0, negative square root of 2, etc. Now, I could draw L negative 2 in there also. It would look like this, about like that. L negative 2, and this would be the point 0, 2. And I could spend all day drawing these level sets, but instead, L negative 2, let me move on to drawing in red the gradient vector function. Okay, so where would it be easy to evaluate x negative y? At 0, 0. The gradient vector is 0 there. Okay, fine. How about if we go out to the point, how about this point right here that's already drawn? Square root of 2, 0. Okay, so if I put square root of 2 in there and 0 in there, then I get the square root of 2, which don't hold me to it on the length, but for the direction, this is square root of 2 comma 0. Okay, points only to the right, and as usual, that is orthogonal to, normal to, the tangent line to the level surface right there. Okay. And where else could I evaluate x negative y real easily? Say up here at 0 square root of 2. That would give me the vector 0 for x, 0, and negative square root of 2. Yes, pointing, again, don't hold me to the length because I don't want to make a really ugly drawing, But this vector right here points in the negative y direction only, and that does indeed look like it is normal to the tangent line to the level set right there. Okay, and where else could I evaluate this? It's pretty obvious to me that, say, at 0, -2, I'll get a vector going that way, and down here I'll get an even longer vector going up that way. Here I'll get a longer vector going that way, a longer vector going that way. Over here I would get a -2, it's negative square root of 2 is 0 coming out of here. That'll point like this. And over here even longer, pointing like that. Okay, so all these vectors that I've drawn so far have been on the axes, either the x-axis or the y-axis. Let me try to go off the axis. Let me look along the line L0 up here at the point square root of 2, square root of 2. Right there. Okay. So what am I going to assign to square root of 2, comma, square root of 2? That point. Well, the vector square root of 2, negative square root of 2. So I should point to the right, square root of 2, and then down square root of 2, and that would give me this vector. Yeah, right there I would get the vector. Where can I label this where it won't be just awful? That vector right there is, okay, square root of 2 comma negative square root of 2, and it's pretty clear to me that that is orthogonal to this level surface, that is L0. Okay, so I feel like that's going to continue to be the case. I'll get longer and longer vectors following L0 out like that. Boy, I could check this pretty much wherever I want. Dare I be ambitious enough to try to find another point on L1, say out here where things look neat and clean? What would be maybe right there? A place where neither x, neither x nor y was 0, and we have that x squared minus y squared is equal to 2 times 1. So let's see. Ooh, wrong color. I wanted to do this in black. I want to find a point that satisfies x squared is equal to 2 plus y squared. All right. Well, let me think about that for a second. If I want x to be a negative number, how about if I'd say x is negative the square root of 2 plus y squared, and then I'll pick a y value. Where y value did I pick? That kind of looks like the y value 1. So let me put a point in there, something comma 1. Okay, so we're going to be looking at the negative of square root 2 plus 1 squared, which is the negative square root of 3. Okay, so interesting. Negative square root of 3 will be the x coordinate corresponding to that y coordinate right there. And then let me try to figure out what kind of red vector to associate that. I should have negative square root of 3 in the first component, and in the second component, negative 1. Right, since I put this in for x and that in for y. Okay, so negative square root of 3 in the first component, that will take me off to the left about square root of 3, and then negative 1 down, that will give me a vector pointing like this, which indeed feels like it is normal to this surface. Okay, that's a pretty busy drawing, and nevertheless, I am convinced by exploring around in this drawing that the gradient is everywhere normal to the level sets of this function. Well, let's see, one more time. The gradient of this function is everywhere normal to the level sets of this function. Yeah, that felt better.